electric effect, right? If I'm saying that I have two different metals and they have different threshold frequencies, I want to know, well, why would they have different threshold frequencies?
It's because in some the electrons are more strongly attracted to the
That's the answer. Okay, that's the answer. Some metals hang on to their electrons more strongly. The nucleus has a better hold, so you got to give them more energy to get them off. It's as simple as that. Eric, make sense? Questions at all? Joe?
With the definition, the minimum frequency that below which the photoelectric effect does not happen.
That's fine.
Particular metals are-
That's, you're saying, yeah, it's just 6 of one, half dozen of the other. Saying the same thing. Questions? Any other questions concerning number 7? Okay, in that case, number 8, you had to go ahead and give Planck's equation and identify what the variables were and explain its significance. So, all right, Ada, you're up. What's Planck's equation?
So E equals H times nu.
Okay, tell me what these variables represent.
So E is the energy of photon.
Good job, yes. H
H is Planck's constant.
and nu.
Nu is frequency.
Okay, good. So we know what the formula is, we know what the variables represent. So what? What's the big deal about it?
Well, when radiation is emitted, transmitted, and absorbed in quanta, it's emitted, transmitted, and absorbed in quanta, that's determined by the frequency of the radiation and the value of Planck's constant.
Okay, you are giving me the implications of this formula from its inception when Planck first introduced it. What I want to know is, what is the significance of Planck's equation today, now that Einstein has added to what Planck already had said? Do you understand?
Okay.
So in other words, I want you to look at this from the big picture as of today, why is this important? Not according to what Planck was saying. It has bigger implications than what Planck had originally stated. You understand what I'm looking for?
Yeah, I think so.
Okay, but what the answer is, that's a different issue.
Yeah.
Okay, so help her out. What do you say, Maria?
It helps give the size of quantum radiation, and then it led to the photoelectric effect.
No. Didn't lead to the photoelectric effect. All right, Samantha.
I said that it showed that the energy of radiation is directly proportional. Oh, sorry, wait. Oh yeah, it was directly proportional to.
2.
For some reason, I did not finish the sentence.
That's an issue. That's a problem. Okay, all right, look. Hunter?
Directly proportional to frequency.
That you attend movies?
Of the radiation.
Need to say that. Okay, and it's more than just that. Because you said the quantum of radiation that's absorbed. You're going back to what Planck originally said and to what Ada was saying, Samantha. It's far more reaching with what Einstein added to. What we need to say is this, okay? There's 2 statements you want to make, okay? First of all, this equation is rather revolutionary. It implies that EMR, okay? So this is the first statement. It implies that EMR can be wave-like in nature. It implies, this equation implies that EMR can be wave-like in nature. Up here, guys, check it out. Frequency, that's a wave property. So it implies that EMR can be wave-like in nature, and at other times, emphasis at other times, okay, not at the same time, and at other times, it can be particle-like in nature. Again, up here, guys, stands for what again, Ada?
Energy of
A photon is particle-like. Okay? So this is implying that EMR, okay, electromagnetic radiation, light, can be wave-like in nature, yet at other times it can be particle-like in nature. Okay, that's the first thing you want to say. So we're talking about this new dual nature of EMR. How it can be, one at a time it can behave as if it were waves, and at a time it can behave as if it were particles. The other importance in this equation is specifically, so the next statement you'd want to make is specifically the energy, not of the radiation absorbed, the energy of the photon. Okay, we want to come straight out and say it because has far greater implications. The energy of the photon is directly proportional to the frequency of the wave. And as Hunter pointed out, you do need to say of the wave. Okay? The photon itself does not have frequency. Some people mistakenly think that the energy of the photon is directly proportional to the frequency of the photon. No, it does not. The photon is not the thing that has frequency. The wave has frequency when it's behaving as a wave. The EMR is behaving as a wave. So again, specifically, the energy of the photon is directly proportional to the frequency of the wave. Questions? In number 8 and 9 and 10, it says, what is Planck and Einstein's contribution to quantum theory? That's an easy question. Their contribution is simply this. They said that EMR can be wave-like in nature, and at other times it can be particle-like in nature. Specifically, the energy of the photon is directly proportional to the frequency of the wave. In other words, the answers to question number 8 is the answer to question 9 and 10. Questions? Yes, Nova.
Were we supposed to separate it by who did what?
No, we are not going to make that distinction on the test. We're just going to take them together collectively, just to simplify things. Other questions? Okay, number 11. How did Einstein explain line spectra? Abby.
Einstein claimed that light could still act as a wave in his explanation of quantum theory, and therefore that Renner's equation is still applicable to EMR.
Does that make sense to you?
Somewhat, but I don't think it's right.
Yeah, okay, all right. First of all, Einstein, how did Einstein explain line spectra? Don't write this down. But he didn't. He explained it a little bit, but he didn't fully explain it. Now here's what I mean by that. Line spectra, so Einstein said this. He said line spectra was the result. So this is what you need down. Line spectra is the result of the electron absorbing or emitting specific photons. Einstein maintained that line spectra is the result of the electrons absorbing or emitting specific photons. Line spectra is the result of the electrons absorbing or emitting specific photons. Each photon has associated with it, a specific frequency which corresponds to a line in the line spectrum. Each photon has associated with it a specific frequency which corresponds to a particular line in the line spectrum. Again, line spectra is the result of the electrons of the atom absorbing or emitting specific photons, and each of those photons has associated with it a particular frequency. Again, going back to Planck's equation, E equals h nu, each photon has associated with it a particular frequency which corresponds, which matches up with a particular line in the line spectrum. that makes sense. You understand what I'm saying?
Well, when he says that it has associated with it,
When I say it has associated with a specific frequency, I mean that each photon, when the same EMR is behaving as a wave, will have a particular frequency associated with that particular photon.
okay, so,
And that frequency matches up to one of the lines in the line spectrum.
okay,
Now, we were talking about the lines in the line spectrum by wavelength, but technically we should be using frequency.
so would it only be able, would a substance only be able to absorb the specific frequencies that corresponds to the length?
Yes, exactly.
So why aren't there gaps? Like, why,
So it's a great question. Abby's saying, well, wait a second. Why is electrons only absorbing certain photons and not other photons? And therefore, only certain frequencies are matching up into a certain line. What's going on there? That's what I meant when I say he didn't explain that.
okay,
He said, look, I can tell you what I think line spectra is due to. It's due to the electrons. And specifically, it's the electrons absorbing photons or emitting photons. And each of these photons have associated with them a specific frequency, which matches up to the line in the line spectrum. I don't know why the electrons are only absorbing these photons or emitting these photons and not absorbing or emitting other photons. He wasn't able to explain that. It depends on the material. And why is it? I don't know. So he did not give us a full explanation. He gave us a better understanding, though, about how line spectra is generated. Okay, before I was like, well, the substances absorb certain frequencies and not other frequencies.
Good morning, Revere High School. Pardon this interruption. At this time, would all ninth grade students letter
The
A
frequencies
to
it absorbs
HA,
or emits,
take your computer.
they match up to a
and
particular line in the line
update
spectrum.
your letter.
That's what we
Again,
thought.
all ninth
That's
grade
what we knew.
students,
Einstein
letter
comes in
A
and says,
to HA,
yeah, it is a little bit more
Here's
to
the
it.
library for not
It's-
training. Thanks.
When a substance absorbs a certain frequency, really what's happening is it's the electrons that are absorbing or emitting photons of energy. That's what's going on. And these photons have associated with them a particular frequency which corresponds to the line and line spectrum. So he gave us just a better understanding of how the line spectrum is actually being generated. He could not explain why the electrons were only absorbing certain photons and not other photons. Yes?
When you say emitting photons, you mean like bouncing back photons?
Emitting means to give off. So if you excite a material, give it energy, so when we did and put the glasses on, you saw an emission line spectra, okay? What we were doing is giving the atom energy. Specifically, we were giving the electrons. The electrons on those atoms were giving off, we're giving them energy, and as a result, those electrons were then emitting photons out towards us.
They're just like creating them?
No, they weren't creating them, they were giving them off. Now, when they do that, the electron loses energy. So the electron was in a heightened state, an excited state, because we've given them energy. And so when it gives off those photons, they go to a lower energy state. Yep.
why would the photons have like different frequencies?
Well, because Planck and Einstein had shown already that the photons don't have frequencies. Okay, the photons have frequency. The wave has a frequency. Frequency is a wave property. EMR apparently can behave if it's particle-like, and at other times it can behave as if it's a wave. And when it's behaving as a wave, it has a certain frequency. Now, it just so happens that when it's behaving as a particle, okay, energy, the photon, the energy of that particle, the energy of that photon, is directly proportional to the frequency of the wave of that particular type of EMR when it's behaving as a wave.
Okay, so if, like in the problems we did where we like drew the photon, that wave would have like one frequency, right? Like one color of light would have one frequency.
Right. A yellow photon would have associated with it a particular frequency. So if I have yellow photons coming down with 50 units of energy, okay, they're coming down. When it's behaving as a wave, it would have a particular frequency associated with it.
So if Einstein's explaining line spectra by saying each photon has associated with a specific frequency, like that corresponds to a particular line in the line spectra, why would like the photons from the same wave have different frequency, like correspond to?
The photons and the waves don't happen at the same time. The light either manifests itself as a wave, it's behaving as a wave, or it behaves as a stream of photons. It can't behave both at the same time.